for Downs, talking about global coronal modeling at SDO scales and linking magnetic complexity to coronal heating and solar wind structures.
Great. Thanks, Laurel. And thanks, Dan. That was an awesome talk. So let me go full screen here. Yeah, Dan did a really good job setting me up for some of the stuff that I'll talk about here. And yeah, Katie, I can address that question at the end. So I'll get right into it. Yeah, so this is sort of modeling work that we've been doing at Predictive Science, trying to sort of get to higher and higher resolution scales with our MHD models. Of course, the short answer to Katie's question is the sun has a heck of a lot more points than we do. But anyway, so just for some quick context, SDO launched when I was in about halfway through grad school, and I was studying EUV waves. And so I had been used to seeing movies of EUV waves where they're very fast. You know, you see a big bright front go across the sun, and both the resolution and time cadence weren't what SDO can offer. And so, as Dan pointed out, I really think it's the unique combination of global coverage, high spatial resolution, rapid time cadence, spectral coverage, and then of course data accessibility that really was this total paradigm shift for me in terms of my scientific interests and how I viewed the phenomena that I was studying. And so I'll just play this short video, which I think really emphasizes it well. Here, I hope this is coming through okay. This is a process video by Miloslav Druckmuller of this really beautiful eruption that SDO saw. And because you see everything at high resolution all the time with this temperature coverage, you can really see this type of eruption in a completely different way. There's sort of rarefaction from the initial eruption. There's stuff falling back down, and you can look at the global context and the local context simultaneously. But now getting into the science that I'm talking to you guys briefly today, is this idea, certainly motivated by the encounter missions that we have right now, that we really want to link what's going on in the solar corona to the solar wind. And so Dan pointed it out well. SDO told us so much about what's going on in the low corona, but then how does that connect out into the heliosphere? And so just the basic problem overview, of course, is we've known for many decades that the solar corona is the source of the solar wind. And we know, of course, that coronal plasma is strongly coupled to the magnetic field. But we also draw these very, very simple cartoons. You know, the sun at minimum is the simple dipole with helmet streamers, right? But in reality, we know that the corona is highly structured and multi-thermal. And SDO, of course, told us how important that kind of stuff is. And so, as Dan mentioned, I really think the next sort of frontier region is this sort of middle corona, which we see very well, of course, during an eclipse. And these process images of an eclipse, it's sort of like SDO for the middle corona in terms of spatial resolution. And I've just sort of highlighted different things that you see. You know, there's this amazing set of structure that we see when we have the full observation and the spatial resolution that we have. Streamers pinching off, things overlapping, open and closed fields sort of existing simultaneously. And so in this talk, I want to sort of illustrate how you can use numerical models to explore this type of idea. And in particular, I'm asking the questions, well, how does magnetic field strength and structure in the low corona influence something like coronal heating and solar wind acceleration? And then really, what happens when we incorporate high resolution information in our global models? And I don't have time to get into the details of all this type of modeling, but the basic overview is that we're doing full global calculations in MHD, resistive MHD of the global solar corona. And I call it thermodynamic MHD because we're adding the thermodynamic terms that are relevant to energy balance in the low solar corona. So that's electron heat conduction, radiative losses, and coronal heating. And once you put all of those types of ingredients in your model, then you can start comparing it directly to observations. And I'll sort of illustrate that with this simple diagram here, where the two most important inputs that you can have to this type of model are your magnetic field boundary conditions. If you're doing a case study, it's of course the surface magnetic field that sets the base morphology of the solar corona. And then it's your coronal heating model. And it's that interplay between coronal heating and the magnetic field that will then influence the plasma distribution in the solar corona and the morphology as well. And from all that, then you can look at things like the magnetic field structure in your model, but most importantly, you can forward model observations, things like UV emission, spectral lines, look at temperature sensitive ratios. Of course, this is motivated heavily by the multi-filter information that SDO gives, and then also look at things like morphology and solar wind. Now, the case study that I'll be talking to you guys quickly here is our effort to look at the 2019 total solar eclipse. And I sort of show this visually, where when you want to do an eclipse prediction that we did, you start off by sort of benchmarking your model at a lowish resolution, a medium resolution, where you're trying to dial in your approach for coronal heating and how you build the magnetic boundary conditions, like what are the polar fields, for example. And then when you get close to the eclipse, you really make a lot of effort to get the best magnetic data that you can so that your morphology will look reasonable. We also have an approach for adding energy to the corona, at least along polarity inversion lines low down. And then from that, you get your sort of final model. We go to higher resolution and make a prediction. And then that prediction can be compared to what is actually seen. But in doing all of this, doing medium resolution simulations, high resolution simulations, we really noticed that when we go from medium resolution to high resolution, the models start looking different in some fundamental way. So interesting structures start appearing in our magnetic field mappings, our forward modeled images, and you want to ask, well, why? So I'll sort of illustrate that. I wanted to get at that and go even higher than we've ever gone before in terms of resolution. And so the way this kind of works is you have some sort of source magnetic field map that could be very high resolution. HMI is even higher resolution than this, but this is a map I prepared at 1800 points in longitude over the full sun. And what you see is there's this sort of nice character of salt and pepper field, sort of the small scale magnetic field structuring is present in a map at this resolution. But then if I want to run an MHD model, I have to, of course, smooth it down to the grid that I have. So over on the right here, this is a medium resolution. You see that much of that high resolution is smoothed out. So now we're left with sort of the macroscopic magnetic field structuring at the surface. Here is the high resolution map that we used for our final prediction. It advanced too quickly. And then here is now with many more points in phi, so 550 more points in phi, we start seeing that there's more magnetic field structure that you can preserve at the surface in your MHD model. And of course, the question is, well, is this important? So I'll try to illustrate that here. So what I did is I wanted to disentangle between model resolution and boundary condition resolution. So for the medium and high resolution cases that I'm showing you, they're the exact same grid, the exact same parameterization. The only difference is the magnetic field boundary condition. And what I'm showing you is the forward modeled AIA images, and then also a forward modeled polarized brightness. And so I'll tab back and forth between the medium and high resolution simulation. And perhaps this isn't too surprising, but we see that a little bit more structure seems to appear in our forward modeled images of the low corona. And the overall morphology in white light is very similar. It maybe gets a little brighter, and I'll go into that in a second. But it doesn't look like it changes that much. Well, now we can go to our super resolution. So now this is 5 times as many points than our very high resolution eclipse prediction simulation. And more importantly, the boundary condition has about a factor of 2 better angular resolution. And so tabbing back and forth again, we see that smaller and smaller scales are now present in the low corona. And then there's sort of this subtle change in the white light. And so if I go back and forth between the 3, you can start seeing the differences as well further out. But of course, as Dan pointed out, this is an MHD model. It's not limited by limitations of our satellites, right? So we can change the perspective and sort of forward model whatever we want. And so now I'm showing you a polar view of this medium resolution simulation. And then the same thing on the right, now AIA 171 forward modeled out to 4 solar radii and radially detrended. And so if I tab back and forth between the high resolution and medium resolution model here, now you start seeing that interesting stuff is happening. So this very smooth polar coronal hole here, all of a sudden gets structures. There's even little plume-like features that we're seeing top down. And then we see plume-like features develop in our forward modeled 171. Now the morphology is very similar in the streamers, but there's sort of little details showing up. And now when I go to super and tab back and forth here, again, you see more and more detail is showing up. So I've added information at the surface that's then propagated into the low corona and now created structuring that's going out into the extended or middle corona. And I think that's really important to emphasize. So again, going back and forth between the 3. And I can zoom out even more. Again, this is an MHD model. And now I can compare that forward modeled EUV emission and put that directly next to polarized brightness. And so this is out to 6 solar radii now, the same sort of views, going from medium resolution to high resolution to super resolution. And I'll just go back and forth again. And the thing to point out here is that even at 6 solar radii, the structuring is changing as we go to higher and higher resolution. So we see little sort of streak-like features in 171 are corresponding to things in white light further out. And we're getting more and more of that structure as we go further out. And then I can tab back and forth and change what wavelength I'm looking at. And you see that indeed, even this extended middle corona is multithermal. And depending on what wavelength you're looking at, it may correspond to different things that you see in white light. And again, I think that type of thing is really important to emphasize, and we can do that with this type of modeling. So then, of course, you want to ask, well, what's going on? Why is this happening here? And for that, I turn to magnetic complexity diagnostics. So I don't have time to really get into that. I can refer to you to these papers down here. But basically, we're doing a volume rendering of a magnetic field line mapping diagnostic, where this squashing factor Q becomes large where there's discontinuities or strong changes in the magnetic field line mapping. So of course, it's going to emphasize separatrices and the streamers and things like that. So this is now going from medium to high resolution to super. Of course, we see that the large scale morphology is there, but structures appear in our magnetic field mapping. We can zoom in. And again, the overall structure is similar, but now we see these sort of cellular features are appearing in our magnetic field line mapping diagnostics. So if I compare this image here to this image here, there's just more and more information. And what's interesting is it really starts to look like coronal loops as we're looking at this high resolution magnetic complexity diagnostic. And I don't think that's a coincidence. Of course, I can zoom in on that and show you what's going on at the poles. And what you see at the poles is we sort of see this sort of classic little pseudo-streamer morphology where you have a parasitic polarity in a unipolar field, but now at very, very small scale. So this is this jet type morphology where there's a spine going out. And we see that as we go to high resolution and include these parasitic polarities, those features are present in the magnetic field mapping. Again, not surprising, but it is important. And now what I want to show you is how this boundary condition looks like at the polar coronal hole. So now for the rest of this, I'll focus on great, getting there. As we go from medium resolution to high to super, we have these parasitic polarities present in our polar coronal hole. I can look at the squashing factor Q, and now we see instead of one big smooth region of just open field mapping from the coronal hole, there's sort of details emerging, these cellular, almost granulation-like looking patterns emerging in our magnetic field line mapping as we go to high resolution. And what's interesting is now I can look at the plasma properties. So now I'm looking at the overall volumetric heating rate low in the polar coronal hole. So this, of course, is the heating rate that then will determine the base densities for something like your solar wind. And indeed, at high resolution, it's becoming more and more structured. There's contrast depending on what position you are in this polar coronal hole. So there's a connection now to the photospheric magnetic field and the complexity of the mapping directly in your coronal heating rate. And no surprise, if there's information or structure in your heating rate, well, that will then relate to your electron density. That's what I'm showing here in purple. And we've known for a long time that the magnetic field can help dictate the hydrodynamics for coronal loop or solar wind plasma. But this is really emphasizing how essential that may be at high resolution. But then, of course, what you really want to know is, well, how does this connect out to the solar wind? So what I've done now is I've gone from this low corona view 1.05 solar radii to now showing you full sun slices at 3 solar radii. And the first is this slog Q diagnostic. So this is a signed version of the squashing factor that has been used to illustrate complexity in the equatorial fields or the SWEP. But in fact, information in the magnetic field mapping is present at all latitudes and comes essentially from that polar coronal hole at these high latitudes. And now I can show you electron density at 3 solar radii. And indeed, there's structure and contrast at all latitudes at high resolution because of that information in the photospheric magnetic field. And of course, if we want to connect it to something that Parker might measure, you can look at the solar wind velocity as well. And indeed, there is structure in the solar wind velocity set by information low in the solar corona. This is a quantitative plot just illustrating that these quantities, whether it's heating, density, low in the corona, or density at 3 solar radii, the histograms or the contrast of these properties are changing with resolution. So to summarize, well, what did we learn from all of this? Well, as we go to high resolution, we begin to resolve sharper features in the closed and open corona. These features are related to the surface magnetic field and its complex mapping into the solar corona. And I think what's really important to emphasize is that this complexity doesn't go away. It maps through the middle corona into the solar wind. And just as a last aside, before I finish, I want to show you why I think this is so important. So what I've shown you is a steady state MHD model. I don't have any time dependence in my lower boundary, but we of course know by looking at HMI or AIA or any movies of these observations before, the sun is constantly changing. There's supergranulation, there's granulation, and flux emergence at an inordinate range of scales, from the small scale and rapid to the large scale and slow. And so I can illustrate that with why time dependence might be very important at high resolution with a very simple experiment. So now what I'm showing you is I'm going away from MHD and just showing you a potential field mapping of a coronal hole somewhere at the equator. So this top row is a potential field that's decently high resolution, but you can see the boundary condition here. It's the same resolution everywhere. And our coronal hole, which is overlaid with this blue, this is open magnetic field mapping. And here's the S-web here. It's sort of this big contiguous feature. But now if I put in super, super high resolution patch of magnetic data, that same coronal hole in the potential field source surface calculation is now highly fragmented. There's disconnected regions in that coronal hole and fragments corresponding to the high resolution flux in there. And then we see that there's information in that magnetic field mapping here that I'm showing you here. So that's now present at the source surface, that information. But now I can go 24 hours in the future and I'll tab back and forth between these frames. So that large scale, low resolution simulation, that big version of the coronal hole, yeah, it moves a little bit, it evolves, but no big deal. But now if I look down here, we see that this fragmented patch of coronal holes, it's really moved around in a number of ways. So certain fragments have gone away, some have come back, and there's changes in the details of this mapping. So the overall morphology doesn't change, but inside there's changes. And so why I think that is really important is what I hope to show you is that with this high resolution steady state MHD model, I've illustrated how the base state of the solar corona would be very, very sensitive to the boundary condition or your model resolution. But as we know, the surface is always evolving, especially at smaller scales, they're evolving rapidly. So we know that as that base state is changing, of course, it will be propagating that information out into the solar corona. And I know I'm going kind of quickly here, but why I think that is really, really important is here's a movie from Craig DeForest's 2018 paper where he sort of brought out all the inhomogeneity that we see with the stereo coronagraph, stereo core 2. And what you see is that there's time dependence and ubiquitous changes everywhere. It's not just at the open closed boundary, but it's virtually anywhere you look in the solar corona, or the heliosphere rather, we see time dependent evolution and changes. And what I hope to convey here, what I hope to argue here is that this information, this high resolution information of magnetic complexity in the low corona, as it constantly evolves, it should necessarily imply constant evolution out into the heliosphere. And so I sort of see that as the next frontier in this type of science. And thank you for bearing with me there. And that's all I'll say.
Thanks, Cooper. That was some really amazing graphics and information and really interesting. We only have about a minute and a half left. We have plenty of questions in the chat that we won't be able to get to right now, but we can discuss it after all of the talks and the breakout sessions. For now, one of the first questions was from Gary Allen about, do you include any transverse magnetic field measurements into your models at all?
We don't. I mean, that's difficult to do all the time, especially over the whole sun. So this is a line-tight MHD simulation where we're only constrained by we're using the radiomagnetic field. nonlinear force-free models and things use that transverse field data driving. That's something we really want to do. You can derive an electric field based on the time-dependent evolution of the transverse field and things like that. But we have not incorporated that in this model. No.
Okay. Thanks. I think we probably need to move on, but Cooper, if you could take a look at all of the great questions and comments in the chat and see if you can address some of those, that would be wonderful. All right, our next speaker is Sabrina